Okay, to start this lecture, we need to do a proposition here that really should have been done as part of the previous lecture, but it didn't, so here it is. So let me state it first, and then we'll review how it's connected to what we talked about at the end of the last video. So it says let J in a kind of an affine coordinate ring be an ideal. And we want to consider its locus at x in AN and its closure x bar in Pn. All right, so here I'm thinking of AN as being a subset of Pn in the way that we were talking about last time, right, where x1 through xn maps to 1 x1 through xn, where these are now homogeneous coordinates. Okay, so that's just the setup. And here's the statement. We have that x bar is equal to the projective vanishing locus of the homogenization of J. And part B tells us how to compute the homogenization of an ideal, of a principal ideal. So if J is generated by a single element, okay, so non-zero principal ideal, ideal, then x bar is just equal to the projective vanishing locus of the homogenization of F. Okay. Okay, so let's do the proof. So for part A, the first observation we need is that VPJH is closed and contains X. It's clear that it's closed because it's a vanishing locus. Why does it contain X? Well, we already talked about that up here. Let me scroll back up to what we were talking about last time. When we were trying to prove that AN and U0 here is the subset of Pn where X0 is not 0. When we were in the middle of that proof, we showed that X is equal to VP of JH intersect AN. So of course X is contained in VP JH. Okay, so that's exactly the observation we need. Okay, let's scroll back down to our proof. Okay, but we want to show that actually VP JH is the closure. So let's let X be contained in an arbitrary closed subset Y. Any closed subset can be written as VP of J prime for some homogeneous, we can assume it's a homogeneous radical ideal. And we just need to show that Y actually contains VP JH, right? And then that would show us that VP JH was the smallest closed subset containing X. Okay, now of course this is equivalent to showing that J prime is contained in the radical of JH. Right, we can assume J prime was already radical, and then we take the ideal of both sides, the inclusion reverses, and we have to add a radical onto the ideals. Okay, so let's try and prove this inclusion here. So any homogeneous element of J prime can be written as x0 to the g fh. All right, so I think we talked about this kind of briefly last time. But if you dehomogenize an element and then rehomogenize it, then the only thing that might happen is that you lose some factors of x0. So that's kind of what's going on here. So you can think about why this statement is true. All right, and then let's see if we can show that x0 ddfh is contained in the radical of jh. So x0 dfh equals 0 on x in Pn. That's our first observation. Why is that? Well, that's clear since x is supposed to be contained in y, and this thing is in the vanishing locus of y. All right, that implies that f equals 0 at every point of x, we're considering it as a subset of an. Okay, and this is because x0 equals 0 on x in an. I mean, this is basically this observation that we made up here, right? So let's remember this: f of 1, x1, x2, dot, 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 xn equals 0 is the same thing as saying that fi, the inhomogenization, is x is equal to 0. All right, so that's basically what we're using. All right, and now OneNote's being funny. Let's see if we can get it to load. There we go. All right, here's our stuff. Okay, but that tells us that f to the m, or that f is in the affine ideal of x. Oh, and x is the vanishing of j. So the ideal of the vanishing is equal to the radical. Okay, that's our standard facts about vanishing loci. The definition of the radical, that means f of m, f to the m power, is in j for some m. Okay, and that tells me here, I'm going to write fhm equals fmh is in jh. Okay, this first equality is because homogenization respects the multiplication. We talked about that in the last lecture, so it commutes with multiplication, so it commutes with taking powers. And then the homogenization of j, well, f to the m power is in j, so its homogenization is in homogenization of j, right? Okay, well, if fhm is in jh, that's the same thing as saying that fh is in the radical of j, h, like this. Okay, and then of course, if you multiply an element of an ideal by anything, in this case I want to multiply by x 0 to the d power, that will still be in the ideal. Okay, and this is what I wanted, right? Because I'm trying to prove that any homogeneous element of J prime is actually in the radical of JH. Okay, and it's good enough to do any homogeneous element because J prime is a homogeneous ideal, so it's generated by its homogeneous elements. All right, so there's a box for done. Okay, now let's prove part B. So let's remember what part B says. Part B says that if J is a non-zero principal ideal, then if you want to take the projective closure, you can just take the homogenization of the principal generator, and that'll do it. All right, so let's do the proof of that. This one's not too long. So the ideal generated by f is just the set of all f times g, where g is something in the polynomial ring. Okay, so that means the projective closure x is equal to VP FG H such that G is in the polynomial ring. All right, this is just part B that we just barely proved. We're just taking the homogenization of this ideal here. Okay, now let's apply our rule that homogenization respects to the product. So it just looks like this. Okay. And finally, we can see that this is just equal to the vanishing locus of FH. Why? Well, in order to check these are the same, we just have to check they generate the same ideal. But that's clear, right? So any FH times GH is in the ideal generated by FH. And if you take G equals 1, then FH is in that ideal. So no problem. Okay, one thing that I haven't said yet, but I should have said sooner, is that X bar is called the projective closure of X. So let me write that down. Projective closure. Okay, let me make a remark about this part B. So let's go back to here. You might be wondering how part B is different from part A and what's the interesting content of that. So let me just give you an example. The point is that it's not always true that you can just take the homogenization of generators of an ideal and then get the thing you want. So let me give an example. So let's have GA be the ideal x1 and x2 minus x1 squared, like this. And we'll have x be the affine vanishing locus of GA in A2. All right, what is it? Well, x1 has to be 0, right? But then x2 is equal to x1 squared. So that has to be 0 as well. Okay, so there's only one point in x, and so its projective closure is not very interesting, right? If you just take the projective closure, it's just the one point again. So x bar will be just the point 1, 0, 0. Right, so in A2 it was the point 0, 0, and so we just put a 1 in for the x0, and that's what we get there. Okay, but if we tried to find the ideal of this just by taking the homogenization of the generators, we would do something like this. We take x1 and we take x0, x2 minus x1 squared. Okay, and it's easy to see this point is still in there as desired, but there's an extra point that we didn't want. If you take a 0, 0, 1, so this is when x0 is 0 and x1 is also 0. Then you can easily see that that's in this vanishing locus. Okay, that's too big. That's not what you want. Okay, so what's the sort of solution? Is you need to use something called a Grobner basis. So a Grobner basis is a basis for an ideal that's particularly nice for many types of computations. So if you've done stuff with computational algebra with polynomials, then Grobner basis is the thing that you always want. That seems to work good. So if you know about that, great. If not, we won't talk about it too much more in this course. But the point is there is a nice computational way to handle this problem. Okay. We're almost done with this chapter of the textbook. Before we finish, I want to just make one comment about potentially confusing thing. So we've talked about two ways in which affine space and projective space are related. So we just finished talking about AN as a subset of PN, where if you have the vanishing of some ideal here, you can take its projective closure, V of JH. So we'll think about this as X goes to X closure, and or if you started with a homogeneous ideal over here, you could take the dehomogenization like this. So this would be something like taking x and mapping it to x intersect an. Okay, so those are the kind of things here. But we also had another correspondence between affine space and projective space. So an plus 1 minus 0 had a map to Pn. Okay, where the fibers of this map are exactly the lines that the Pn is parameterizing, right? And in this case, we had a nice bijection. If you took the projective vanishing locus here, then that corresponded to just taking the affine vanishing locus of the same ideal, and you get some kind of cone here. All right, and here we had a bijection. Between cones in an plus 1 and projective varieties. Over here, this is not quite a bijection, right? Because you could have something like the vanishing locus of x0 over here, and that would correspond to the vanishing locus. Well, if you dehomogenize x0, you just get 1. So this would be the empty set, right? Okay, that makes sense, right? This is just vanishing locus of x0 is exactly sort of the line at infinity that's not included in the an. So if you try and restrict that back to the an, you get nothing. Okay, so compare and contrast. These are two different things, but two different ways where you can relate affine space and projective space. In the last chapter, we just treated projective varieties as topological spaces. But in this chapter, we're going to give them the structure of ringed spaces and show that they are actually varieties. All right, so let's quickly review our notation. So x in Pn will be a projective variety. S of x will be the quotient of the polynomial ring in n plus 1 variables by the ideal of x. And remember, the ideal of a projective variety is the ideal generated by the homogeneous functions that vanish on x. Okay, and remember that S of x is a graded ring. Okay, and of course, if x is just itself Pn, then S of x is just the polynomial ring. Okay, now and we call this the S of x is called the homogeneous coordinate ring. Now, in contrast to the affine case, the coordinate ring, the homogeneous coordinate ring of a projective variety, the elements of it are not functions on the variety. So let's remember how that worked. So if f was a homogeneous element, so say of degree d, then the vanishing locus of f in Pn makes sense, and that's how we defined projective subvarieties. But f is not a function. Oh, why is that? So if you take f lambda x, the definition of a homogeneous function, this is lambda to d times f of x. So for most values of lambda, these are not going to be the same, even though lambda times x is supposed to be the same as x in Pn. All right, so here's x is a point, thinking of it as a point in an plus 1. Right. Okay. All right, so f is not a well-defined function. Okay, but here's how you can fix this. If you have two elements, f and g, they're both homogeneous of the same degree, then a quotient of them will give you a well-defined function. Because if you take g of lambda x over f of lambda x, you'll get lambda to the d g of x, lambda to the d f of x, and that'll be g of x over f of x. The lambdas to the d's cancel. Okay, so you get the same number no matter if you plug in x or lambda x into this quotient of polynomials. So that actually gives you a well-defined function. So we're going to follow that to define the structure sheaf on a projective variety, the sheaf of regular functions. Here's our definition. Let u in x be open. X is still our projective variety. A regular function on u is a map from u to our ground-filled k, such that now we also have to make this definition local, just like we did in the affine case. So we're going to say such that for every a in u, there is a neighborhood u subscript a neighborhood of a, so that contains a, and then a d, which is going to be a degree in natural numbers, and then f and g, which are homogeneous of degree d, with the function, so let's name the function phi. Phi of x is equal to the quotient g of x over f of x. Okay, and remember g of x over f of x is well defined by what we said just above. And this has to work for all x in UA. Okay, and I guess for this to make sense, we must have f of x not equal to 0 on UA as well. Okay, so this should remind you a lot of our previous definition for affine functions. The difference is that we need to make sure these two functions are homogeneous of the same degree so that we can get something well defined. All right, okay, and then so OX of U will just be the set of all regular functions on U. And it's easy to see this is going to give you a K algebra, right? And if you put these all together, you're going to get a sheaf. All right, this kind of local definition will ensure that it glues nicely, and they are functions, so that makes it pretty easy to check this as a sheaf. All right, so we're going to call this the structure sheaf for projective variety, and that means X together with the structure sheaf OX is a ringed space. Okay, so the first proposition we want to prove about these projective varieties as ringed spaces is we want to show that they're actually pre-varieties in the sense of our previous chapters. Okay, so to show something is a pre-variety, you have to check that it has a cover by affine varieties. So what's the cover going to be? Well, it's going to be these UIs that we talked about in chapter 6. So UI is the set of points of X such that in homogeneous coordinates, xi is not equal to 0. Okay, and the claim of the proposition is that each of these UIs is an affine variety. So in particular, this shows X is a pre-variety. The only thing we have to worry about is whether these UIs cover X, but that's easy because any point of X, at least one of the homogeneous coordinates has to be non-zero, which will let it be in some UI. If all the homogeneous coordinates are 0, then it doesn't count as a point in projective space. Alright, so that's the proposition. Let's do the proof. So by symmetry, we can assume that I equals 0, right? Any argument we make is going to be the same for I equals 0 or 1 or n. So let's just do I equals 0. Okay, and let's assume that x is equal to Vp of j for some homogeneous ideal. And let's let y be equal to Va of ji. So this is the dehomogenization of j with respect to the variable x0. And let me define some maps here. So f will be the map from a y to u0 that sends x1 through xn to O1, and then x1 through xn in homogeneous coordinates. So this is the map that we used in the last chapter a lot. And then we also need the inverse map, f inverse u0 to y. And how does this map work? Well, it takes a point, arbitrary point in homogeneous coordinates, and maps it here in affine coordinates. We just divide by x0. This makes sense because x0 is assumed to be non-zero, so you can divide by it. I'm going to leave you to check that these are well defined and inverse to each other. Those are just some easy checks. And then we also have to check that they are continuous. But we already did this for the case where X is projective space in the previous chapter. That's the same argument. Remember we showed that U0 was homeomorphic to the affine space. Oh, so basically the same argument. We'll give you that this F and F0 are homeomorphism and an inverse together. Okay, so the real thing that we need to check is that pullbacks of regular functions are regular. So that, in other words, the F and F inverse are morphisms. All right, we already have that they're continuous. So let's do the pullbacks. So if I take f upper star, what's a regular function on u0? Well, it's something that's locally a quotient of homogeneous polynomials of the same degree like this. That's the definition we just barely did. Okay, but how does the pullback map work? Well, the pullback map is just to plug in these numbers, right? So we'll have g of 1, x1 through xn divided by f of 1, x1 through xn. But that's just the dehomogenization, right? That's the definition of dehomogenization. And we know that those give us polynomials in the affine coordinate. All right, so this here is gi over fi. That's a perfectly good regular function on y. Okay, so no problems there. Let's now look at f inverse pullback. If we take f inverse and pull back something of the form a regular function on affine space, or on an affine variety, is just a locally quotient of polynomials, like this. These are different f and g's now. Okay, and how do you pull it back? Well, you just plug in the things that in this definition of f inverse up here, right? So we'll just get g of x1 over x0, x2 over x0, over f of the same points. Okay, and then we have to check and see, is this a quotient of homogeneous polynomials? Well, what you have to do here is multiply. I mean, these things here look like they're kind of rational functions in the variables because you are dividing by x0. So what you need to do is clear the denominators. You need to multiply by x0 to the d. So let me just write it like this. Okay, of course these are equal. as x0 is not equal to 0, so it's okay to just multiply the fraction on the top and the bottom by the same thing and it's still equal. And we need to take here d to be the maximum of the degree of f and the degree of g. Okay, and the point is here, x0 to the d times g of x1 over x0 and so on. That will be a homogeneous polynomial because g, when you plug in these, will give you something of degree 0, right? And then once you clear the denominators by multiplying by x0 to the d, you'll get a homogeneous polynomial. Okay, but then now we're pretty much done, right? Because we pulled back a quotient of polynomials and we got a quotient of homogeneous polynomials, both of degree d. So that's a regular function. Okay, so we're done. So f and f inverse are morphisms and inverse to each other. So that shows that y is isomorphic to U0. End of proof. Okay, so we've seen how projective varieties have are examples of pre-varieties that have kind of a nice global description. So now our next lemma is going to show us that morphisms of projective varieties can also have kind of a nice global description where you don't have to worry about gluing things together. So here's our lemma. We're going to pick f0 through fn to be elements of Sd of x, so there are homogeneous polynomials all of the same degree. Okay, and let's let u be x minus the vanishing locus of these f's, and we'll see in a minute why we need to do that. And then the lemma says that we have a morphism and actually, sorry, let me change this n to m. I'll reserve n to be the dimension of the projective space that x is in, and m means something else. We have a morphism U to Pm, the projective space of dimension m, that's defined by taking x to f0 of x, f1 of x, all the way up to fm of x. All right, so this dimension of this projective space matches up with the number of f's. Okay, so let's do the proof. So first we observe that this map is well defined. By construction of U, the point 0, 0, 0 is not in the image. All right, so that would be a problem. If all these f's vanished at a single point, then you would not have a well-defined map because this is not a point of projective space. Okay, and of course, maybe you can choose these f's so that they generate the irrelevant ideal or something, and then you would then you'd be okay and you wouldn't have any vanishing locus to worry about. Okay, but there's another thing we have to worry about too, because we have to worry about whether the image is well defined if you choose a different representative of f, but that also works out okay. So let me write it down like this. So if we have f of lambda x dots up to fm of lambda x, that'll be lambda d f0 of x to lambda d fm of x. Okay, but as a point in projective space, we can cancel off the lambda d's and just get this. All right, so this shows if you picked a different representative of the point x in projective space, by multiplying by lambda, you still get the same point in the image. And the key fact here was that these were all homogeneous of the same degree. All right, so the last thing to check is that this is actually a morphism. So to do that, let's let vi be equal to the set of where yi is not equal to 0, considered as a subset of Pm. That's the image, and yi will be the generators of the homogeneous coordinate ring of Pm. Okay. And then we'll let ui just be the inverse image of the vi. And let's think about what this map looks like. What does f look like restricted to ui? Now thinking of it as a map from ui to vi, and then thinking of vi as isomorphic to an affine space. Okay, well, it just looks like this, right? It takes x and it maps it to f0 over fi dot dot dots. Okay, and then there'll be something like fi over fi, but you want to leave that one out, right? So this little hat means leave that out, and then go all the way up to fm over fi. All right, this is just the isomorphism that we saw in our last lemma, and remember how the affine, we identified these subsets by just we identified u0 with affine coordinates by dividing by x0 here. Okay, so we're just doing the same thing over here. Okay, the point is here that f0 over fi up to sorry, and this m here should be a subscript, of course. f0 fm divided by fi these are regular functions. On ui, by definition, right, they're quotients of homogeneous polynomials of the same degree. So f is a morphism. At least on ui. And then the ui's cover the source, so it glues together to a morphism. Okay, remember this was a lemma we had a while back, that if you're looking at a morphism to am that's given by regular functions, if the coordinate functions of the map are given by regular functions, then it's a morphism, right? Okay, so that's what we're using here. Let's just do one example, and then we'll call it good for the day. So let A be an invertible matrix in GLN plus 1 over our field K. Then you can take F to be a map from Pn to Pn, defined just using the lemma that we talked about just a moment ago. So that will be a morphism. Okay, and what's the definition? The definition is we take x and map it to a times x. Okay, and you see that is exactly of the form here, right? So each of these f's will be degree 1. It'll just be, you know, a11 times x1 plus a21 x2 or something like this. That'll be you know, that'll be correspond to the f0 and so on. Okay, and then the nice thing about this one is it has an inverse. Given by just using the inverse matrix. So clearly those will be inverse of each other, but once again that's going to be a morphism. So this is an automorphism. Automorphism meaning an isomorphism of a variety with itself. Okay, and these are called the projective automorphisms. Okay, it turns out you can show that, in fact, these are the only automorphisms of Pn are ones that are given by matrices like this. We won't prove that, but we might use these projective automorphisms again sometime. Okay, let's call it good for the day.